Okay, so it's 5 minutes past the hour, shall we?
Yeah, I'm ready to
So,
go.
uh, just for a brief introduction, the main topic of today's presentation is related to web fonts, something that we all by now are very familiar with, but the web fonts present some additional challenges because for some of us, especially people who are in China and Japan, font sizes are still a big issue, and that's something that is a big technical problem that needs a solution. The proposed solution is something that we will discuss during this presentation, and I would like to present our speaker, Rieger. He's a software engineer on Google Fonts team. He's been there for 7 years, and for all these 7 years, he also been a very active contributor, participant, and since last year, also a co-chair of the W3C Web Fonts Working Group, which is, he's been nominated and approved, appointed for this position, which is a big accomplishment and also big credit to his efforts and also to his contribution. So I would like to welcome him to give us a presentation on the new subject that is part of the new charter for the Web Fonts Working Group development. And without further ado, Garrett, take the helm and let's dive into the incremental font transfer.
Great. Yeah, thank you for the intro, Vlad. Let me just get the slides shared here. Okay, looks like we're working. Okay, great. Yeah. So Vlad already introduced me, but if you need that all again, here it is, who I am. Okay, yeah, so first let's just take a quick look at what I'm going to talk about today in this presentation. So to start off with, I'm just going to give a quick introduction to what incremental font transfer is. I think not everybody may have encountered this before, so we'll just do a quick refresher on that. Then I'm going to go into a more in-depth look into how the incremental font transfer mechanism actually work and how we're going to implement these. Then next, I'm going to talk about, we set up and did a simulation of these incremental font transfer methods in order to get a better understanding of their performance. So I'll talk about how we did that. And then lastly, I'm going to be presenting the results that came out of that simulation. Okay, so yeah, what is incremental font transfer? So it's a way to load fonts, which is able to load just the parts of a font that you need to render some content. And so this may sound familiar to font subsetting, which has been used for a long time, but it is different in one kind of fundamental way, and that's that you're able to add content to an existing subset of a font to increase its coverage. So with subsets, if you had one subset of a font and you wanted more data to render additional characters, you would have to get a different distinct subset. And that has some drawbacks, which we'll talk about. But first, just a quick example to kind of illustrate what this actually looks like. So let's say we have some page that we want to view, and it has the word meows, and it's rendered in a font. And so we want to minimize the amount of data we're going to load. So we're going to load a subset of the font that just has those characters in it. And so far, everything's working great. Let's say, though, we go to a second page. It now has the word awesome rendered in the same font. So if we try to reuse the initial subset, it's going to be missing data for a few characters, like, for example, the capital A, the lowercase m, and another interesting one is the kerning data between the E and the W will not be there. So with incremental font transfer, we can add data to that original subset for those characters and that kerning rule that we're missing, and then we get a new version of the font, which can now render the text on that second page. Okay, so this sounds kind of interesting, but why is this something that we actually need? So most importantly, this allows us to only pay to transfer the parts of a font that are actually needed for any given piece of content. So it's quite common for many fonts to support multiple scripts, but any given user is probably going to only need one or two of those in practice. So there's no point in them paying to transfer all this additional data for parts of the font that they're not going to use. And this gets even worse for languages like Chinese, Japanese, and Korean, whose fonts have tens of thousands of characters, of which you maybe only need 1,000 or so for any given page. And so this, for those fonts, is actually a huge barrier to using these as web fonts. So having a way to only take what we need is really important. So to date, the way that this has typically been solved is by using a subsetting-based approach. So you take the original font, you split it into different subsets, maybe by script or some other strategy. But this has one big downside, and that's that you can run into problems where there's layout rules that span those subsets. So for example, if you have 2 characters in 2 different subsets, you can't have a kerning rule between those anymore. So incremental font transfer, by building up a single font, allows all of those layout rules to just work always without problems. And so this, this technology, it promises to be a way that we can remove some of the existing barriers to using web fonts, especially for things like CJK. To give an example of that kerning problem I mentioned, so at the top, let's say we've got a font that has a Latin and Cyrillic script support. So if you have a single font, you're going to get a rendering of that text similar to the top one. Now, if we break it into a Latin and a Cyrillic subset, it's going to look more like the bottom one, where in green is the characters that are rendered from the Latin subset, and in blue is the characters rendered from the Cyrillic subset. And you'll notice that the kerning between the period from the Latin subset and the Cyrillic character is off. So this isn't that bad, but for more complicated scripts, this can create like real readability problems with things just being completely rendered incorrectly. Okay, so we've got this idea for incremental transfer. This could be just implemented in JavaScript and be used today, but unfortunately that is not going to be as fast as it could be. So ideally we want this technology to run in the browser natively. Now to make that a reality, we're going to need standardization. So that way this technology can operate across all the different browsers. And so the good news is that we are actively pursuing the standardization of this with the W3C Web Fonts Working Group. All right, so that's kind of the high-level overview, but let's look at a little more detail on how this actually works under the hood. And so as it turns out, there's actually 2 completely different approaches to do this. And so I'm going to explain both of them, since they're both kind of being actively considered. All right, so the first approach is called patch subset, and the name derives from the fact that you're applying patches to an existing subset of the font. All right, and so how this works is, so you've got a client, and then so they've got some existing subset of the font. If they want to extend it, what they do is they send a list of code points that are in the subset that they currently have to the server. And then they send a second list of code points, which is the ones that they want added to the subset of the font. Then the server will cut 2 subsets kind of on demand, one that will match what the client currently has, and then a second one which will be what the client wants, so what they already have plus those additional characters requested. And then the server is going to compute a binary difference between those 2 subsets, which will produce a patch, and then that patch goes back to the client who can apply it to their subset to get the new extended one. All right, so this relies on 2 kind of really important pieces of technology that kind of came about recently, which made this method a possibility. So the first thing is this method, because it creates subsets on demand in response to a client request, you need an ultra-fast subsetter, something that's working in the millisecond range. So that way you're not introducing unnecessary delay for the client waiting for that patch to be computed. So we use the HarfBuzz subsetting library, which is written in C++ and was designed to be ultra-fast. And so that actually recently, just yesterday, kind of became, we did like our 1.0 release where it fully supports all of the major subsetting operations. And then the second part is we need a way to make really compact patches between two binary objects. And so there's a bunch of different ways this can be done, but we found that the Brotli compression library, which supports binary patches, produces extremely small and compact ones. So that's what we're using there. All right, so I've got a demo of this that I can show. And so let me get that shared. There we go. Okay, we can see that. Okay, and so just to explain a little bit, so what we did is we implemented both a client and a server in C++, and then I took that C++ client and I compiled it with WebAssembly and got it running in browser. So ideally, this would eventually, that client part would be built into the browser directly, but for now, just for the demo, it's running as WebAssembly. Okay. Oh, and so just to explain a little bit more, so this demo, as I go through the different pages, it's going to load fonts using the patch subset method, but it's also going to use fonts using the Google Fonts API as it exists today. And then on the right-hand side there, you're going to see a comparison of how much data was transferred by those two different ways of doing it. Okay, so let's go. So we go get our first piece of content, and then so this fires off two requests, which you can see here in the network tab on the right side, to grab data for that font. And so that only took 17 kilobytes to get the data to render this text, whereas the Google Fonts API would have sent you a single subset that was 32 kilobytes. And so you can see that in the second tab here, where you get one font file for each of the two fonts being used. Okay, so we go to a second page, and so you'll see now it fired off two more requests, which added another about 3 kilobytes of data, and that added any characters that would have been missing for that font that's in this text here. Okay, and so on as we go through content, you'll see it's just slowly adding additional characters as they're needed. And you'll notice, and so this is all happening in real time, it's actually sending requests, and you'll notice how fast this is. Like you can, there's barely any delay in getting the font in. Okay, so that was Latin content. So now we hit some some Vietnamese text. And so on the Google Fonts API, we have the Vietnamese stuff separated off into a separate subset. So you'll notice that the Unicode range total jumped up by another about 30 kilobytes as it pulled in a whole other font file. However, this was able to just patch in those additional characters that are needed to the font that was already there. Same story again for Cyrillic. This triggered another subset needing to be loaded if you're doing the existing Google Fonts way. But here we're able to just grab a small patch to get more support. And so on. And this is actually a good place. So I can hit this button, the Show Unicode Range, which will flip to show the text as rendered by the Google Fonts versus the patch subset. And this demonstrates the kerning issue that I talked about. So you'll notice if you look at the period and the Y against the Y in the top title there, as I flip between the two, it's actually in the wrong place. So this is just an example of some of the problems that you can solve beyond just making things faster and send less data. Okay, now the more interesting case, let's look at some Chinese text. So this, again, is using Google Fonts to load the fonts in the background. And this is using some of the work that we talked about a couple of years back, where we've aggressively subset the Chinese fonts down into about 100 subsets and load what's needed, which already is a significant reduction of what you would get if you loaded the full font, but it still needs to get quite a bit of data. In this case, about 700 kilobytes. Whereas with incremental transfer, we were able to load just a fairly small patch in comparison to support this content. And then as we go through, the gap just gets bigger. So the Unicode range approach is downloading additional subsets as new characters are being encountered, but it's pulling in more data than with incremental transfer, which can very exactly target the characters. Okay, great. Yeah, so that's the demo. We'll get back to the slides now. All right. Okay, so that was the first method. The second method we call range request, and the name for this comes from the fact that this utilizes HTTP range requests as the mechanism to do the incremental transfer. So this is quite a bit different than the previous approach. So in this version, what you do is you take your font file, and then you need to do a little bit of optimization on it. So the most important of which is you need to take the glyph or the CFF table, whichever it has, you need to move it to the end of the file. Also, it helps if you reorder the glyphs in that table so that frequently occurring ones are closer together. So then what happens is, so the client, say you start a new session to load this font, so they download all of the font up to the point where the glyph table starts. So once they see the glyph table data start coming in, you just stop the request and you stop downloading anything. Then the client uses the part of the font that is already downloaded to figure out what glyphs are needed to render the text. So it goes through, does all your shaping and all of that, and then actually gets the glyph indexes that are needed. From there, it can use the loca table to determine the byte ranges that the glyphs of interest exist in that glyph table. And then it can use HTTP range requests to grab just the data for those. And then so then effectively you just have all of the spaces for the glyphs that you don't grab just end up as being like zeroed out in the glyph table until you grab data for them. Okay, so let's talk a little bit about kind of what the trade-offs between these two approaches are, because they both do things very differently, and that means different things. So first, one of the real big benefits of the range request approach is it's extremely easy to deploy since it doesn't need any kind of specialized backend server. So you can just take your optimized font and you can throw it onto basically any HTTP server, and it will support incremental transfer with this method. And so this is pretty important because a lot of content or people who are putting content on the web may not actually control their server backends. They may just be, putting their stuff up on a CDN or using a third-party hosting of some sort. So having a method which they can use without having control over their backends is important. And the additional benefit of that is since no server-side computation is needed, this is going to be a little bit lighter, like in terms of CPU cost to run this solution. The bad news, though, with range request is it's only capable of incrementally loading glyph data. And so for some fonts like CJK, that's fine because the vast majority of the data in the font is in the glyph table. But for other fonts, like say an Arabic font, they can have a significant amount of the font file size is taken up by non-glyph data. Like for example, a whole bunch of layout rules can often take up quite a bit of space. And so patch subset is able to incrementally transfer data across all tables in the font, not just the glyph data. Another nice advantage of patch subset is that by using this Brotli patching mechanism, you effectively get compression across requests. So data that came in a previous response, you can actually compress against that in a future response, which keeps things extremely small. Okay, so we've got these two different methods, and so what we wanted to do is we wanted to understand how they actually perform in comparison to each other. So we decided that we wanted to build a simulation of font loading, and then that we could just put in all of these different ways of loading fonts, and then it would tell us, how these actually performed in kind of some representation of real usage. So there's two main questions that we wanted this simulation to answer for us. So the first was, does incremental transfer outperform existing font transfer methods? Because if this isn't improving on existing things, then there's not a lot of point in adding all of this complexity to font loading. And then the second question is, of these two incremental transfer methods that I just discussed, which actually has better performance? Oh, and I should clarify. So when we say performance here, we have a specific definition for that, and that's the user experience due to font delays, font loading delays. So if the user has to wait 100 milliseconds before they can extra before the page renders because of the font loading delay, that would be like worse performance. We would define that as being worse performance than something that took less, that had less of a delay. Okay, so we want to simulate font loading and we want it to be realistic. So we need kind of a realistic model of the network transfers. And we need some realistic representation of kind of a user moving between and viewing pages that have a bunch of content loaded and rendered in fonts. And then we need the actual font loading methods that we're simulating to be fairly realistic representations of those. All right, so the first thing we need for the simulation is we need some input data to drive it, and we want that input data to be kind of as realistic as possible. So the first set of data that we needed was on network conditions. So we decided to model network transfers as with two parameters. So that's the bandwidth of the connection and then the round trip time. And then so to get some numbers for these, we actually gathered real world connection speeds from Chrome. Just across a bunch of users using Chrome. And then we took all of that and we categorized it based on the underlying connection type. So the categories that we ended up with were 2G, 3G, 4G, Wi-Fi, and desktop. And this is kind of a catch-all for like sort of broadband type wired connections. Okay, and then the second kind of input data we need is going to be this sequences of page views. So again, we were able to gather some data from Chrome, and this what we ended up was kind of like an abstract representation of content being viewed. So we have a sequence of pages where each page is just a set of fonts, and each font has a set of Unicode code points associated with it that we want to render from that font. All right, so then we looked at that input web corpus, and we categorized it by which language the text in those pages was using. And then we split the data set into three groups by grouping languages that we thought would have similar behavior with respect to incremental transfer. So the first group is Latin, Greek, Cyrillic, and Thai. And so this group is characterized by scripts that generally have a small number of code points and fairly simple or kind of low usage of layout rules between those code points. And so then I have a graphic here showing the actual breakdown of languages that's in this grouping. The second grouping is the Arabic and Indic scripts. And so these we categorize as, again, having a relatively low number of code points, kind of in the hundreds, but with kind of very complex layout rules between the characters in these scripts. And so again, here's just the breakdown of the actual specific languages that are within this group. Okay, and then the last group that we had is for Chinese, Japanese, and Korean, and this is characterized by scripts that have extremely large numbers of code points, often I think in the tens of thousands or more. Okay, and then the last piece of this puzzle is the actual font transfer methods that we want to simulate. So first, let's define what we mean by a transfer method. So a transfer method takes some set of fonts. It takes the code points for each of those fonts that you want to load. It takes a model of the network, so that's the round trip time and the bandwidth that I previously mentioned. And then it outputs how much time would be needed to load the fonts using that transfer method, and also how many bytes were transferred to make that load. And so this tries to be a fairly accurate accounting of the bytes. So we account for things like, the HTTP header overhead and kind of like all of those additional bits of overhead beyond just the actual font bytes that you're sending. Okay, so first we simulated a couple of existing methods. So this would be ways that fonts are transferred on the web today. So the first of which we call whole font. So what this does is when you need some code points from a font, you just load the whole thing all at once. And then on subsequent page views, you would just reuse that previously loaded font from the cache. And so this probably represents how most people would use web fonts today. The second one is called Unicode range. And so here the font is going to be split into a bunch of script-based subsets. And then those are loaded as you have code points that are needed from the individual subsets. And again, these would be reused from the cache on subsequent page views if possible. And so this, I think, is less common on the web today, but for example, the Google Fonts API makes heavy use of this strategy. Oh, and I should mention the subset definitions that we used were from the Google Fonts APIs. Okay, and then the two new methods that we simulated were the patch subset and range requests, which we've previously talked about what those are. Okay, so we've got kind of all the input data to drive it. We've got the methods to simulate. Now we need to look at how we're actually going to evaluate the performance in the simulation. So the simulation outputs two main metrics. So one is the total loading delay for each method across each network and each script grouping, and then also the total number of bytes transferred. So total loading delay is a little inaccurate if we wanted to just use that directly as the final cost metric. So we actually apply a cost function to that metric to get the final cost. And so the reason for this is that, so let's say, for example, you've got a page, some stuff happens, and it's going to render after some time. So if you can complete your font load before that initial loading time where other things on the page are loading, then it has that delay, that font loading delay isn't going to have any impact on the actual amount of delay that the user sees. So in our cost function, we have this initial area here where if your font loads before that, it incurs little to no cost. And then from there, after this cost start line, the value of the cost function raises non-linearly. So we penalize extra long delays, very heavily. So we're looking for methods that load very quickly, within that initial window. And then finally, at some point, most browsers will give up on a font load. So after about 3 seconds, if the font hasn't loaded yet, it'll time out and it'll just render as a fallback font. So having a loading delay go beyond that point doesn't really negatively impact the user any more than it already has because the browser has just moved on. So that is how we ended up with this shape for the cost function. And so this is what we're using as the primary metric to evaluate the different loading methods. Okay, so with that, let's actually look at some of the results. Okay, so this first graph, this is how much the bytes transferred was reduced using one of these transfer methods in comparison to just sending the whole font for Chinese, Japanese, and Korean. So here a higher value is better because that means you're sending less bytes total. And so what we're seeing here is pretty much across all of the different connection types, we're seeing that patch subset is producing the most reduction in bytes sent by far, with range request not too far behind. And so typically it's looking like about 90% bytes reduction versus just sending the whole font. And so the Unicode range approach is actually doing quite well here, which is what we would do today on the web and reducing it by 50%, but we're beating that even by quite a bit with the two incremental transfer methods. And then one interesting thing you'll notice here for 2G, patch subset actually had less reduction. And to explain, one kind of optimization that we do with the patch subset approach is that depending on the network conditions, so if you're on a very slow network with a large round trip, in response to a request, we'll send more code points than you asked for back in the hopes that we can prevent you from having to make a future request, which would have a very large penalty on that round trip time, which means that in general, you end up sending more bytes. So that's why for this 2G, this is actually lower. Okay, so that was the bytes transferred. Then let's look at the cost. And so this is the same thing. This is the reduction in cost versus whole font. So here, higher numbers are better. And we see a pretty similar pattern to what we saw with bytes. So with patch subset coming up with the largest cost reduction, range request in second, and Unicode range in third. Now here we see some interesting differences once we get down into the 3G range. So here, range request and Unicode range actually did worse than sending the whole font. And this again comes back to that round trip time I was talking about. So on slow networks like 3G, round trip times are very high. So sending more requests than something that sends less requests is going to result in a much higher penalty. And so because for patch subset, we have this mechanism that actively tries to reduce the number of requests that are being sent, it was able to still do good in this 3G area, whereas the other two methods ended up doing worse than just sending one single font, which minimizes the number of requests. And then I've broken out the 2G graph into its own graph here because it's so far into the negatives that it skews everything off. So here we see for 2G that any of the incremental methods and Unicode range really don't do good at all. And this is, again, due to that extremely high round trip time penalty. So here your best bet is to just send one request, even if it's a really long, slow request, because any future request just takes so long. Okay, so that was CJK. So now let's look at Arabic and Indic. So CJK was kind of like the best case for incremental transfer. I think we, from the get-go, we knew that that would be one where we would do quite well in. So it's going to be pretty interesting to see kind of what happens with these other scripts, which are much smaller and have less opportunity to benefit from incremental transfer. So again, here we see that incremental transfer does quite well. So specifically, patch subset pretty significantly outperforms the Unicode range approach. It doesn't have nearly as much reduction as in the CJK case, but this is expected due to the fonts being smaller here and generally needing higher proportions of them. Interestingly, the range request does a little bit worse than Unicode range. And I think this probably comes down to the fact that it can only incrementally transfer the glyph data. So it's missing a lot of opportunity to actually optimize over Unicode range. Okay, and then next is cost. Okay, so here we see kind of some mixed results. So in some cases, patch subset is doing a little worse than Unicode range. In other cases, it's doing better. And then for range requests, the story is much different. It's pretty much universally doing worse than just sending the whole font. And so this is definitely an interesting outcome. Oh, and again, I've split off the 2G into its own graph because similar to CJK, we just see the two incremental methods do quite bad on the 2G connections. Okay, and then the last group, Latin, Greek, and Cyrillic. So the story here is quite similar to Arabic, where we're seeing the patch subset do a little bit better than Unicode range in terms of bytes reduction. The overall reduction is pretty similar to Arabic. We're seeing about a 50% in general. And then again, range request is just kind of doing worse than either of the other two methods. And then again, a similar story for the cost functions. So here, Unicode range is beating it out in some cases. In other cases, incremental transfer, depending on the connection type, and range request just kind of universally doing worse. Okay, yeah, so let's talk about the conclusions that we can draw from all this. So let's go back to those two questions that we wanted answered at the start. So does incremental transfer outperform existing font transfer techniques? And I think it's a pretty clear yes, with one caveat, and that's not on 2G. So on 2G, it was pretty universally bad. But for all the other connection types, it was definitely a viable transfer method. In many cases, it outperformed Unicode range, and when it didn't, it was quite close in performance to it. Plus, it has the additional benefits that you get, like correct rendering, which is something that you lose with Unicode range. And the second question, so of the two incremental transfer methods, which performs better? So again, this is a pretty clear answer. Patch subset throughout all of the results outperformed range request. However, to be fair, the performance isn't everything that we would consider when picking a method. So range request was one very big, but very important benefit over patch subset, and that's deployment is much easier. So this method is going to be much easier for people to use than setting up like a custom server that's going to drive the patch subset approach. So that creates some other problems. So how do we decide which of these two methods we want to standardize? We know we have, on one hand, we have patch subset, which has really good performance. On the other hand, we have range requests, which is going to be much easier to deploy. So after a lot of talking about this, the working group, we decided that we actually want to standardize both of these. Because both provides meaningful kind of advantage. And like in particular, range request could be a huge enabler for CJK fonts because it's very easy to deploy for people who want to use it, and it gives very good benefit for loading CJK fonts. But on the other hand, you have, say font services or people who are willing to invest a bit of extra effort to get every last bit of performance. Patch subset is a very attractive option there because it kind of universally provides improvements. Now, to make this all easier on users of the technology, we designed a transparent negotiation mechanism. So that way you just set up your server with one of these two methods, and then your CSS or whatever is the same regardless, and it just figures out what the server's doing and works with whatever the server's capabilities are. So that way it's really simple to use. And so just to give an example of what actually using this would look like in your CSS, you would have a font face that would look something like this. So first you would have just a standard URL to, like, say, a WAF2 version of the file. So this would be for clients that do not support any sort of incremental transfer. They would just use this WAF2 link, and everything would just kind of work the way it does today. And then for clients that do support incremental transfer, we use the new CSS supports mechanism here to say that this is an incremental URL. And then the server or the client would then talk to the server, figure out which method it supports, and then use that method to do the transferring. Okay, lastly, let's just talk about kind of what the future looks like, what we're going to be working on next for this. So now that we've settled the question of what we're going to actually standardize, we're going to work on actually writing the specification. And then the second part of that will be all of the conformance tests. That's part of the specification writing process, which turns out is quite a bit of work. So I'll call it out as its own thing here. Kind of in parallel to that specification work, we're working on developing an actual in-browser prototype of this, so one that's implemented directly in a browser natively. So we have the demo I showed, but we want to see how this works actually directly in the browser. Then we're actually also in the background continuing to just work on further optimizing the performance of these incremental transfer methods. So finding additional ways that we can make them faster or more compact. And then one last kind of interesting area is so far I've just talked about incrementally transferring code points in the font. But this technology doesn't need to be limited just to code points. It's set up in a way that it can incrementally transfer any data in the font. So if we look at something like variable fonts, this is quite interesting because, for example, we could incrementally transfer deltas. So as you need different parts of the design space, we could pull that in on demand instead of having to load entire axes all up front. And so this, for variable fonts, especially multi-axis fonts, with 3 or 4 axes, this could be a huge optimization that would allow for much smaller transfer sizes for variable fonts and could be a huge enabler to allow these to be used. So this is a really interesting area. I'm kind of excited about exploring this and seeing what more we can do there. And then there's also potential we'll have to look, there might be other parts of the fonts that might make sense to incrementally transfer beyond just the variable data. Okay, so that's all I have. And so we can do, I think, some question and answer now. And then I've also just got some links here to some various parts of this if you want to learn more. So we've got the specification, as I mentioned, is in progress. So there is a draft version of this already up on GitHub. It's pretty early stages, but it is making progress kind of continuously. Then I've got the link here for the demo that I showed, which is publicly accessible. You can go over, open that up, and play with that if you want.
Yeah, there was a question asking to share this link in chat window.
Oh yeah, let's do that. That is a good idea. I'll give you 1 sec. I will get these pasted. Oh, was there a specific one they wanted, or I'll just throw all of them in here?
I think the demo itself.
The demo? Okay, yeah, that's the most interesting one.
Yeah, and then we have a collection of questions by now. So let me just try to go back and see what hasn't been covered yet as part of the presentation.
Yes, absolutely.
First question comes from Lawrence regarding the specific method for requesting and delivering subsets, PET subsets. So what protocol will be used for?
Okay, yes. So yeah, what we're doing here is we've defined a custom binary encoding. Well, I shouldn't say custom. So we're using a serialization protocol called CBOR. And then that's just like a generic message serialization. And then we use that to build that request message that contains the information that the client is going to ask for. So the set of code points they have, the set of code points they want. And there's also some additional stuff like checksums that kind of make sure everything lines up. So if you do want more details about that, that is contained, the specification has some of that already. But also I guess if you wanted to, you could actually look at the simulation code, would be kind of the authoritative source on that so far. Well, I should point out, so the link here, probably the interesting one. So the evaluation report has a more in-depth look at all of the data I shared today and a write-up of kind of, how we interpreted that. So that's definitely, if you want to learn more about the simulations, the evaluation report would be a good place to go. Okay, other questions. Okay, so we got the demo link. First in-browser version might be available. So I don't have an exact timeline on that. That's pretty early stages. We're just beginning that exploration, and so it's unclear how much work it's going to be to get this integrated into something like Chrome. But maybe, hopefully, sometime this year, if that all goes well. And then there's another question here asking if we're in contact from people from Firefox, Apple, Microsoft about this topic. And the answer is yes. So as part of the W3C Web Fonts Working Group, we have members from, specifically on this list, we have members from Apple and Microsoft who have been participating in the development of this specification. And so the range request approach is actually was proposed by Apple. So that's where that one came from. Okay, so then we have a question. Have you tried this with scripts beyond the first 64 Unicode numbers, SMP? I don't think we've specifically tested with those, but there's no reason that it wouldn't just work. So as long as your subsetter can support subsetting that font, which it definitely would, then it just works just the same as any other font.
And also in the chat window, there was another question from Paul Underland regarding the variable fonts support.
Okay, let me see if I can find that.
I'm having a hard time trying to scroll back and find it, but I remember seeing it. Yep. The question was regarding tests, were they conducted with variable fonts or static fonts?
So the tests were conducted with both, actually. So the library of fonts that we used, I forgot to mention this in the presentation, but we took all of the fonts in the Google Fonts open source collection, and that was the set of fonts that was used in the simulations. And so that includes a mix of static and variable fonts. For those variable fonts, we didn't do any instancing or anything. We just used the full with all accesses versions of them. So we do want to, as I mentioned, we want to do some more exploration in the variable space to see if it makes sense to like incrementally transfer the variable parts of that font as a separate mechanism from the code points. Okay. Oh, I see one other question here in the chat. So applying this to VF predicates using patch method though, or is there some way of structuring the VF to work with the range method? So that's a bit trickier. The range request method works the way it does because the glyph table is structured in a way that all the glyph data, all the data for one glyph is located in one continuous range. So with other tables, like the VF tables, the data can be a lot more scattered about, so it's harder to use the ranges to grab what you need. Potentially with some work, maybe we could figure something out. That is very challenging. Okay, so we have a question here. Oh, sorry, and to answer Lawrence's question, who was asking about the protocol. So we're using just HTTP for the actual network requests. And then, so I have a question here. Could this be used to load a web font with kerning strict and then add kerning upon request? Yes, absolutely. So that's not supported in the current version of the spec, but we actually have talked about allowing the set of layout features that you want to include to be specified by the client. And then so you could use that to, for example, like you could have your tabular nums, you could incrementally add those after the fact if you needed them. Or you could set up similar, you could set up a layout feature which would pull in all of the kerning data after the fact. So that sort of thing could definitely be supported.
Maybe it's worth mentioning that patches, at the time when patches are created, is literally a binary patch. So any portion of the font data that's part of the original and was not part of the subset can be inserted via patch. That doesn't really require.
That's right. Yeah. So yeah, fundamentally, we can increment kind of anything in the font that we can like subset against in a way. So if we can pull it out and then we can later add it on and we can make a patch between those two things, then we can increment it. Okay, oh, and then Lawrence has followed up, so why not sockets? So I think we just wanted to keep things simple and just use like the tried and true HTTP requests. Although I suppose there's no reason that this couldn't be also made to work over sockets, which may provide some additional performance in some cases. So that's actually an interesting idea.
And the new question just came in again from Paul regarding caveats of these methods, whether there are any caveats with this method, and specifically regarding, for example, TrueType hinting.
No, so as far as I'm aware, this should work with basically any existing fonts. So things like hinting just work. You could even theoretically add hinting incrementally if you wanted. Like that is something that could be done. So for example, you could by default not pull in hinting data, and then you could add it later. Another bit that I didn't mention, which this could be used for, would be font version upgrades. So say you've got some version of a font, like let's say it's an emoji font, it's like 20 megabytes. And then you release a new version of your emoji font and you add maybe 100 emoji to it. Today you would have to reship that entire 20 megabytes to the client to update them to the new version, where all that really changed was just like that addition of 100 things. So with this incremental transfer approach, you could actually do that version upgrade just as a patch to what the client already has. So there's lots of really, I think it opens up a lot of really interesting possibilities. Beyond just kind of what we've initially talked about here.
I believe we addressed all the existing questions, and the new questions are not coming in at the moment.
Oh, looks like a couple more just popped up here. Let's see. So for every item that we can say can be added incrementally, does this mean the client should send every time I already know about this subset? Yes, so the way it would need to work is the client would have to describe what it has in a way that the server can reproduce what the client has. So that would have to be part of the messages that goes back and forth. So whatever those things that we want to increment, the client would have to have a way to describe them to the server in a way that the server can reproduce the client's state. And so I didn't talk about this, but we've actually done a ton of work. A large part of the work that we did in developing the protocol was developing a way to very compactly represent code point sets. Because if you can imagine, if you have a Chinese font and you're trying to send a set of code points that's say 5,000 code points in it, and you do it the naive way and just do it as just a list of integers, it's actually massive. Like that's going to be kilobytes of data to send that set. So we did a ton of work to and developed a novel encoding for sets to send them extremely compactly. So typically we can send sets using less than 1 bit per code point sent, which is really cool.
And I shared the link to description of the sparse bit set earlier in the chat. So the link is out there.
Oh, great. That's correct. So so there's a question. The server does not keep track of particular client states. So yes, the design here is the server is completely stateless. So the server does not track clients or remember clients in any way. So the client always describes its entire state on any request to the server, because we wanted this to be as simple as possible to run. So we don't want people to have to run databases or anything like that to track client states for this to work. So we designed it to have all that state encoded entirely in the requests.
So I guess it's useful to mention that there are two possibilities here. One is that because of the limitations imposed by the design approach to have server completely stateless, there's only certain things that can be done when you calculate two different subsets on the fly, and therefore patches that submitted have to rely on those two conditions and two requests being made. But in principle, that from the technology standpoint, anything and everything inside the fund can be patched. So if we later on, if we decide that, for example, stateless approach is limiting and some additional benefits can be achieved by changing that, it's a possibility because the technology behind it does not limit us to only patching something that would have been a complete subset. We truly can just provide binary patch for any part of the fund data.
Okay, great. And I think I just got a notification that we are pretty much out of time. So I don't think there's any other questions. So I think that's probably a good time to end.
And I think it's a good time to remind people that we can actually continue this discussion in the Hangout room. So if we have more questions and want to address them in a much more personable setting when it could be a dialogue, please, you're all welcome to just transition to Hangout room for further discussion. And thank you very much for attending this talk. That was great. Garrett, you did a great job. Thank you.
Yeah, thank you.